So let's look at the area of some quadrilaterals. So the area of a square is the most basic quadrilateral. It's just the side length squared. Then we have the rectangle, which is length times width, and then there's quite a few others that you can also find. But is there a formula for any quadrilateral that you choose? Well, let's find out. So the first thing I can tell you that there is a formula for the area of any quadrilateral. It's pretty simple because a quadrilateral is fixed and there has to be an exact area for that quadrilateral. But the harder part is, how do we find the formula? Well, one way to do it is just to get all the side lengths and then the diagonals, but that is going to be really hard to find. Just like the Heron's formula for the area of a triangle is harder than the normal triangle formula. And we can use the same strategy. Instead, we can use even less variables, and it looks much easier to calculate in this format, because we've simply divided it up into shapes that we know how to use. And we can actually simplify this even further, but I won't talk about this now, that'll be for later. So to calculate the formula for the area of any quadrilateral, we will just be using two basic formulas: the area of a right angled triangle and the area of a trapezium. So now let's get started. We have our altitude and our sides written in, and you can see that the altitude lines already divide the shape up into 3 parts. We know how to solve these parts, so we can just get the areas of these using the side lengths given, and this is our formula, but we can simplify it. So we can make it this and then here, but we can actually simplify this even more. This is where the simplifying down comes in. So let's look at this formula more closely. The S1 and plus S2 and the S2 plus S3 can actually just be changed into just 2 variables instead of 3. So we've simplified our algorithm down further. So this is our final algorithm: A1C1 plus A2C2 over 2. So now let's get on to some examples. So here's our formula. Let's say we have the dimensions. So S1 is 2, S2 is 4, S3 is 2, and then our 2 altitudes are 2 and 4. That means that we can put in the values, and then so A1 is just 2, and then C1 is going to be the first 2 segments combined, so that's 2 plus 4, so that's 6, and then altitude 2 is 4, and then our C2 is going to be 4 plus 2 is 6. We put those together and we get 18. Now we're going to split these into pieces that are easy to calculate and just calculate them normally. So there's our side lengths, here's our areas, and we find that it is also 18. Okay, so it worked. Let's move on to another example. This one is slightly different. So here our shape, instead of going out, it actually goes in. So how do we calculate this then? So altitude 1 is just going to be 2. Combined length 1 is going to be 2 plus 4 here. So this is actually 4 to the second point. So it's 2 plus 4, that's 6. And then altitude 2 is going to be 4. And then combined length 2 is going to be from the second point, which is here all the way to the last point, which is here. So it's this plus this, so that's 4 plus -2. This is negative because it goes inwards. So that's 4 plus -2, that's 2. So we plug in those values, we get 10. And then again, we split them up into pieces, put in side lengths, calculate the area, and we also get 10. Okay, another example. What if it goes all the way to there? So put in the lengths, we got altitude 1 is 2, altitude 2 is 4, its combined length 1 is going to be just 1, it's going to be 6, I mean, so here up to there. Then combined length 2 is actually going to be -1, it goes from here all the way up to there and then back to here. So that's 4 plus -5, that's -1. Then get that all together, we get 4. Okay, again, let's put it all together, and using the simpler way, we also get 4. Okay, so here we have it going inwards on both sides. So then what happens? So altitude 1 is 2, altitude 2 is 4, combined length 1 is going to be just 3, because so it's from this length, this point to here, and then the other one is going to be 2 because it goes from here to there. So plugging the values, we get 7. Now using more simpler calculations, we also get 7. Now this is going to be the last example. So we've got this actually bending in. So then what would happen? So altitude 1 is 2, altitude 2 is 6, and C1 is going to be 2 only because it goes from here up to here. This first one is 4 and the second one is -2. Then the other one is also 2, it goes from here to there. It's -2 plus 4, so then we plug it in the formula, that's 8. Now, how are we going to calculate this? So you might notice this red triangle here. This is actually a right angle triangle, and we can simply use the Pythagorean theorem to get the side lengths and to calculate the area. And then all we need to do is just get this outer area, and we get the area of the white shape. So here are all the shapes in the diagram, and put in the side lengths. Now this is, as I said, it's just going to be 2 square root of 5 because it's 4 plus 16, and it's okay, square root of that. Do the math for yourself if you want to check. Then we can put in the areas, and we also get 8. So I think all these examples should make it pretty clear that this formula works, and it does. So now let's study this formula more closely. So you might see that this looks like the area of 2 triangles combined, and it is actually the area of 2 triangles combined if you just move it around a bit. So let's look at our quadrilateral. Where are these 2 triangles? So pause the video, see if you can find a way to split this quadrilateral up into 2 triangles such that they have the exact length, bases, and altitudes as what we have here. Okay, found it? Well, this is the line where you split it. Okay, there is one obvious triangle, but hey, this is not a triangle. Well, yes, it's not a triangle, but we can actually turn this into a triangle. So here we have it, and we can actually, so look at this part. Because of the same base, same altitude principle, we can actually move this point all the way down to here, and it will still have the same area. So this is where we get our second triangle. And then if we get that other triangle back too, then put in the lengths, it does have exactly what we wanted. So this is a simple explanation of why this formula works. So now let's experiment with this. So because we only actually have two variables, let's just look at this. So it's only this part, and these two are fixed. So that means we can actually move these around this as much as we want, as long as this length and these two stay the same. So we can actually turn it into a shape like this, and it would still have the same area because all the variables here are the same. So even though the shape is different, the area is still the same. And we can go even further. We can go all the way to the end, and again, it still has the exact same area. So that's it for this video. Thank you for listening, and hopefully I'll see you next time.